Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 5. We are in part 8 of chapter 2, and we are discussing simple comparative experiments, or it's also called two-sample tests, mostly the two-sample t-test. So we've talked about those hypothesis tests, the structure of them. We've done 4 different tests with different assumptions. So that gives you all of the possible or readily available or usable options for testing two samples that are independent of each other. All right, that is an important specification there, that they are independent of each other. There's different methods that we use if there is a dependence between the two samples. All right. So now we're going to move to confidence intervals. So I hope this is a topic that you already know, but in case it's not, we're going to do a quick review. So hypothesis testing gives an objective statement about the difference in means, whether they're different or not, but it doesn't tell us how different they are. So that's what we can tell using a confidence interval. And the general form of a confidence interval is given here. L is less than theta and U is greater than theta. You could also say that theta is between L and U. You could say that theta is contained within the interval L to U. And we've set up a probability here that we're going to use in order to solve this confidence interval. However, I have to caution you that you do not want to say this as the probability that theta is between L and U. That is not correct. Even though that's exactly how it's written here, theta is a constant, unknown constant. No probability is associated with theta. So where does the probability come from? It comes from our test statistic, and it comes from specifically the two statistics, y1 bar minus y2 bar, and that has a certain distribution. We could call it y of f of y, and this has a distribution. So that is what makes this statement able to be calculated. And so what we can say is the probability that the interval LU covers or contains theta. That's how we should say this. And this is correct. And so what we're saying is that the interval may cover the true value. So the true value, let's say, of theta, whatever our estimate or our parameter is, when we calculate different confidence intervals, we're going to get different, I guess I should make most of them contain theta. So they should, most of them should contain theta, but some will not. All right. So sometimes theta is in our interval, and sometimes it is not in our interval. So the interval we're saying covers, this interval here covers theta if theta is within it. And so let's say that the point is here, and so this interval also covers theta. This interval does not. This interval does, just barely, and this interval also covers theta. And so theta can be anywhere in the interval. It can be right on one edge of it, or the other edge, or close to one edge, or close to the other edge of the interval, or near the middle. But we don't know. So it's not appropriate to say the probability that theta is between these two values. It's more appropriate to say that the two values cover theta. And so this probability here, which is also 1 minus alpha, is called the coverage probability. Okay. And so we have the 101 minus alpha % confidence interval, and we can use CI to denote confidence interval. I can also write this as 1 minus alpha %, because percentage is a change in units, so I really don't have to say the 100, although many times we'll say 1 minus alpha, and then what people say is 100% as a multiplier. The 100 goes with the percent. But if you just say percent, then that means that you need to multiply by 100 in order to get it to percentage. All right. So it's really a formatting issue. If you want to see an example of this, go to Excel, type in, say, 0.12, and then go up, select that cell, or right-click on it, and then go to Format and select percentage, and you'll see that even though you have typed in 0.12, what's displayed is 12%. So it's really just a format. All right, so here is our confidence interval. We have our difference in means, sample means, and then we have our critical value. And finally, we have the standard error of the estimate. And this is the estimate. If we want to estimate the difference in the means, we'll subtract the sample means. But if we want a range of values, which is much more interesting and useful than a single value, then remember from this picture, the difference in means changes depending on the sample that you choose. And but the range gives us this gives us a probability. If I say, what's the probability that y1 bar minus y2 bar is equal to theta, then that probability is 0 because y1 bar minus y2 bar has a continuous distribution, okay, which is normally distributed or approximately normally distributed depending on the sample size. Okay, so we've got our estimate minus the critical value times the standard error of the estimate, and that is our lower value. And then we have the estimate plus the same term. And so what we can say is y1 bar minus y2 bar plus or minus t alpha over 2 n1 plus n2 minus 2, and then s sub p square root 1 over n1 plus 1 over n2. So this is our estimate, and we would call this theta hat in this case, because the hat is the estimate, not the MLE, but just an estimate. And then this is our critical value times the standard error or the standard deviation of the estimate, and this is called our margin of error. Some may call it accuracy, although that can be misleading, or we could just say error. So we may abbreviate it MOE or E. Okay, so we have theta hat plus or minus E is one way to write our confidence interval. So now let's derive this expression, and we're going to derive it from the probability, the coverage probability statement. So we're going to start with that. And so we have the probability that L, the interval L to U, contains theta is equal to 1 minus alpha, and the test statistic T naught, which is equal to y1 bar minus y2 bar minus parentheses mu1 minus mu2 divided by s sub p square root of 1 over n1 plus 1 over n2. And this has a t distribution with n1 plus n2 minus 2 degrees of freedom. All right. So since we know how this is distributed, we can now substitute into this equation. And so what we can say is, okay, we have the probability that t, that negative t, alpha over 2, n1, I'm just going to call this nu, okay, the Greek letter nu, make it much easier to write, comma, nu is less than or equal to y1 bar minus y2 bar minus mu1 minus mu2 over s sub p square root 1 over n1 plus 1 over n2 is less than, this is a negative, and so then we have the positive, alpha over 2 nu is equal to 1 minus alpha. This works because the t distribution is symmetric. Okay, so the t distribution is symmetric, and that is poorly drawn as symmetric. So let me move it up so I can put my hand on my iPad and get a little more stability. That's still not very symmetric, but we'll just pretend like I drew it better. And so if we have t alpha over 2 and t sub alpha over 2, the negative, this is 0. This distance here and this distance here are the same. And since it's symmetric, this area here and this area here are the same. So the probability of us having this test statistic that is between these two values is, sorry about that, is 1 minus alpha. So the total area under the curve has to add up to 1. Alpha over 2 plus alpha over 2 is equal to alpha, and then alpha plus 1 minus alpha is equal to 1. All right. So our goal here, what we're trying to do is we're solving for the parameter, which is mu1 minus mu2. We're getting that by itself. So the nice thing is that our standard deviation is always positive, so we don't have to worry about changing the inequalities when we multiply across them. So this implies that we have, I'm going to multiply the denominator by all three parts of this inequality. So I end up with negative t alpha over 2 comma nu s sub p square root 1 over n1 plus 1 over n2, and then I have y1 bar minus y2 bar minus, I need to erase my beautiful drawing, minus mu1 minus mu2, make sure you don't forget your parentheses, and on this side it will be a positive t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2. And now I will subtract y1 bar minus y2 bar from all sides, and I will put it in the front, so I have a negative y1 bar minus y2 bar, again the parentheses are very important, minus t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2, and then in the middle I have negative mu1 minus mu2, and then I have minus y1 bar minus y2 bar plus t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2. I need a positive here. I have this wrong. So this is a negative out in the front. I want a positive for this. So because I'm interested in mu1 minus mu2, that expression. So to do that, I will multiply all sides by a negative. When I multiply by a negative, I have to reverse the signs. All the signs get switched. So this implies the probability of positive y1 minus y2, y1 bar minus y2 bar. Now, this also becomes positive, t alpha over 2 nu s sub p, and those are supposed to be subscripts, so I should write them lower and smaller. And then s sub p square root 1 over n1 plus 1 over n2. is now greater than or equal to mu1 minus mu2, which is greater than or equal to positive y1 bar minus y2 bar. But now this positive becomes a negative t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2. And I'm almost done, but this is, we usually put the smaller value here and the larger value here, so we need to reverse this, and when we reverse it, we'll reverse the signs. And so this tells us that we have the probability that y1 bar minus y2 bar minus t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2 is less than or equal to mu1 minus mu2, and that is less than or equal to y1 bar plus or minus y2 bar plus t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2. All right, and so this probability is 1 minus alpha. So the confidence interval, the interval that gives us 1 minus alpha in probability, is y1 bar minus y2 bar minus t alpha over 2 nu s sub p square root of 1 over n1 plus 1 over n2. That's the bottom value, the lower value. This is L. And this, the upper value, is y1 bar minus y2 bar plus the same quantity, t alpha over 2 nu s sub p square root 1 over n1 plus 1 over n2. So, and this is u. So this is the first way to write the confidence interval. And so what we have is theta hat plus or minus critical value times standard error of the estimate of theta hat. And for symmetric distributions, this is the general form of the confidence interval. Okay, so if you can find the critical value and the standard error of the estimate, you can create a confidence interval. The second way to write this is exactly this way, and so we will do y1 bar minus y2 bar plus or minus t alpha over 2 comma nu s sub p square root of 1 over n1 plus 1 over n2, and I need to put nu, this is important, is equal to n1 plus n2 minus 2. Okay? Nu is equal to n1 plus n2 minus 2. And the third way to write the confidence interval is L comma U in interval notation, and this would be y1 bar minus y2 bar minus t alpha over 2 nu, or I'm just going to go ahead and substitute in n1 plus n2 minus 2 s sub p square root 1 over n1 plus 1 over n2, comma, y1 bar minus y2 bar plus t alpha over 2 n1 plus n2 minus 2 s sub p square root 1 over n1 plus 1 over n2. And so then I need to put my brackets to make it an interval. Okay, and because it's easy to write here, we will put, I will rewrite this. Alpha over 2, n1 plus n2 minus 2. And that way I don't have to define nu, but it's short enough to where I don't need to do that. And then I will do the same thing here. Alpha over 2, n1 plus n2 minus 2. And then I need to do it on this side as well. Alpha over 2, n1 plus n2 minus 2. As the degrees of freedom, here I can say nu equals n1 plus n2 minus 2. All right. So that is the derivation. So if we want to plug in the actual confidence interval here, we want the 95% confidence interval estimate for the difference in the mean tension bond strength for the formulations of the Portland cement mortar. We just substitute into that equation. So we need to know our numbers from before. We have y1 bar equals 16.76, y2 bar equals 17.04, s1 squared equals 0.1, s2 squared equals 0.061, and n1 equals n2 equals 10. So the first thing I'm going to calculate is s sub p, which is the square root of s sub p squared, which is equal to the square root of n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2, which is equal to 9 times 0.1 plus 9 times 0.061 over 18, don't forget the square root, which is equal to the square root of 0.0805, which is approximately 0.284, and the book rounds all these values and creates a large rounding error, relatively large rounding error. The computer will not do that. We should not do that, but to be consistent with what the book has, I will do that. And then I also need to find out T alpha over 2 N1 plus N2 minus 2, which is T 0.025, because alpha, this is 1 minus alpha, so alpha equals 0.05. This is percent, so that's 0.95. Okay, so 0.05 divided by 2 is 0.025, and then this is 18. And we found this before in the T table, and it's 2.101. Okay, so we plug into our formula, which was y1 bar, 16.76, minus y2 bar, 17.04, and then minus t, which is 2.101, times s sub p, which is 0.284, times the square root of 1 over 10 plus 1 over 10, which is 2/10, which is 0.2. And we have mu1 minus mu2 in the center. And then we have the same thing. This turns out to be negative 0.28. And then we'll have plus 2.101, 0.284, and square root of 0.2. Once we find this quantity, we know this quantity because they're the same. So this is negative 0.28 minus 0.27, and so mu1 minus mu2, this will be negative 0.28 plus 0.27, and this gives us mu1 minus mu2, negative 0.01, and negative 0.55. Okay, and so again, this is E is 0.27. And so again, we can write this as 0.28, negative 0.28 plus or minus 0.27. This is 1, this is 2, and 3 would be negative 0.55, comma, negative 0.01. Notice that 0 is not in our confidence interval. And so 0 would say that there is no difference between the two means. And since it's not in the confidence interval, we would say that at a 95% confidence level, the mean difference between the difference between the two means does not contain 0, and therefore they are different at a 95% confidence level. Okay. So that is, and sometimes people write this as open brackets. I don't really like this because Well, it doesn't really matter technically because the probability that they're equal to these endpoints is 0. However, we do round things, and so that does happen in actual practice. And so we want to make sure that this interval is at least 95% in this case. So we just want things that are more extreme to be rejected. Okay, to be safe, we try to keep the coverage probability at least 1 minus alpha. Okay, so when we're doing the derivation in practice, what we want is we want this to say greater than or equal to. Okay, instead of just equal to. If we have to err, we're going to err on the side of that confidence being higher, not lower. Right? So the coverage or coverage probability and confidence level, we would rather them be a little higher than a little lower. Okay. So now, I won't read this. This is from the book. So, but I will give you the idea. So the confidence interval estimate, it ranges from or extends from negative 0.55 to negative 0.01 kgf per centimeter squared. Okay, or we could say again that it's negative 0.28 plus or minus 0.27. That method is my least favorite because it requires the reader to do the calculations. So either of the other two are more preferable to me. Okay, so the difference in mean strengths is negative 0.28. And the precision of the estimate is plus or minus, is actually, we just say 0.27 usually, but you can say plus or minus 0.27 if you like. Because 0 is not included in the interval, the data does not support the hypothesis, the null hypothesis, that mu1 is equal to mu2 at the 5% level of significance or the 95% confidence level. Okay, and if you remember, the p-value is 0.04 about 2. Here is the t-test that we had when the variances are equal. So here we had variances equal, is true. And here is our confidence interval that was included in the output. And so for the case when the variances are considered equal, it's about 0.55 and about, or negative 0.55 and about negative 0.01. So these are given to us. And this is the mean of x, and this is the mean of y. Unfortunately, R doesn't always line up things the best way, but that's why we retype it. Okay, and so this was, again, the test code for, or the code for the t-dot test function, which you see here. All right, so I've copied this over again and given you the confidence interval for when variances are not equal. So here we have a new confidence interval. We have the critical value and we have the standard error, but now new is this monster. So the homework is use the relationship of L, theta between L and U, where this is the coverage or coverage probability, and derive the 1 minus alpha % confidence interval for mu1 minus mu2 using the same principles as we just did. Write the answer in 3 different ways. So I've given you those 3 different ways, and I did that in the example, so that will be on your homework. If you have questions, come to virtual office hours. If you need help before office hours, by all means email me. I will get back to you as soon as it's possible. I am happy to help you. Please take care of yourself so we can see you next time.